everyone, welcome to the video. Today I'm going to introduce reconfigurable electronics based on liquid metal composites, the topic of my PhD work. So here, three types of people are welcome to hear. So first, if you don't know liquid metal yet, this is the time to get interested. Second, if you just start to look into liquid metal research, you will learn the key properties of gallium. So you can jump right in. And finally, if you already work with liquid metal, I will share the work I've done, which might bring a different angle to your own. So, welcome, and if you have anything like questions or any ideas you'd like to collaborate on, feel free to reach out anytime at the email here. This presentation starts with the background and material design of liquid metal, and then moves into 3 different chapters from my own work. Alright, let's get started. Our environment is always changing, and living things have evolved to adapt to it. Our pupils, for example, becomes larger when you go into dark to get more light. A sea cucumber is normally soft, but it stiffens its body when a predator catches it. And a cuttlefish can create various patterns in their skin, so it can camouflage itself with surroundings. In contrast, conventional electronic systems are built for a single purpose, and once they are made, their properties are fixed. So, a car's round wheel, for example, work well on a flat ground, but they can't climb over the obstacles. The phone is rigid, which makes it easy for typing, but uncomfortable to wear. And a barcode or QR code can identify an item quickly, but its pattern is fixed, which leaves it vulnerable to copy. To overcome these limitations, reconfigurable systems have recently emerged. This robot can change its shape to climb over the obstacles. This gripper stays soft to wrap around the fragile object like an egg, then stiffens to pick it up and move it safely. And an OTP changes its security key every time you press it, making it far more secure than a fixed pattern. So, thanks to these possibilities, reconfigurable systems are drawing attention across many fields, from healthcare to robotics and security. So, what's exactly a reconfigurable system? It's a system whose function changes in response to external stimuli. Triggers such as temperature, light, magnetic field can change key properties such as stiffness, shape, conductivity, and color. So to build these reconfigurable systems, researchers have steadily developed a variety of stimuli-responsive materials, and here are a few of them. However, these existing stimuli-responsive materials share a common limitation. They achieve reconfigurability, but the properties they catch in each state fall short compared to the fixed materials. Take stiffness, for example. Magnetic composites, shape memory polymers, and hydrogels. They are great and they can switch between a soft and rigid state, but the range they can actually cover is fairly narrow. The material that solves these problems is gallium. To start with, gallium can tune various properties: stiffness, conductivity, and even optical properties, all in a single material. And the range it covers for each one is remarkably wide. In terms of stiffness, around its melting point of around 30 degrees, gallium goes through a phase change. So if it's in a solid state, it's 9.8 gigapascals as hard as a metal, and if it goes to the liquid state, its stiffness drops close to the zero. That's a billion-fold change in stiffness, which was not achievable with previous materials. In terms of conductivity, it's also interesting because gallium itself is a metallic conductor, but the insulating oxide layer forms naturally on its surface. You can remove that layer with acid or put in pressure, which makes you switch its conductivity on and off. It also has low emissivity, which means temperature changes cannot be detected in the infrared range. But when you mix it with a high emissivity material, for example like PDMS, stretching the liquid metal lets you tune how much temperature change show in infrared area, depending on the location of liquid metal. And also, since liquid metal gallium has zero vapor pressure, it does not evaporate, which makes it safe for a wide range of bioelectronic applications. So, the goal of my PhD research was to use gallium to transform traditional fixed systems into reconfigurable ones. However, even though gallium is an ideal reconfigurable material, its actual use in reconfigurable system is still limited. That's because when gallium is used in a bulk state, it runs into mechanical instability, processing difficulties, and functional limitations. Let's look at these more detail. First, in its liquid state, gallium bursts and flows easily under even a small amount of pressure. Second, its surface tension is about 10 times higher than water. It means it tends to merge together, which makes patterning very difficult. And also, its low melting point near the room temperature causes unwanted solidification during fabrication, making the process tricky. Third, as a single bulk mass, it is hard to control spatially or individually. I solved these problems by making gallium into particles. When you disperse the gallium particles in a solution or a polymer, we call it a liquid matter particle composite, or LMPC for short. Here's how LMPC overcomes each of these limitations. First, when bulk gallium is turned into particles, surface tension raises the internal pressure. This is called Laplace pressure, and it's inversely proportional to the radius, which means that the smaller the particle, the higher the internal pressure and the higher the effective elastic modulus. You can think of high internal pressure like a balloon filled with a lot of air. Just as a balloon filled with a lot of air is hard to press, a particle with high internal pressure is also hard to press. So, when liquid metal particles are mixed with an elastic polymer, such as PDMS, you might expect that composite will get softer as you add more of them, since they are all liquid. And with the large particles, that's right, what you think. So the more you add, the lower the modulus drops, and even below of the polymer alone. So eventually, it's more softer than just polymer. But small particles behave the opposite way. Because of the high Laplace pressure, they resist the compression, so as you add more, the modulus actually goes up. Second, turning gallium into particles solves the processing problems. In bulk, its high surface tension makes it merge together, but once it's in a particle form, the oxide shell keeps the particles separated. That's what let us print them at high resolution without any clumping. On top of that, the OH groups on each oxide surface make the particles spread well over the hydrophilic surfaces. And there's one more benefit. The smaller the particles get, the stronger the supercooling effect becomes, which keeps the gallium from solidifying when we don't want it. So supercooling effect will be explained in detail later in Chapter 1. Finally, while bulk gallium reacts as a single unit, particles each behave independently. For example, if you make each particle different in size and composition, they will heat up at different rates when the temperature rises. So to sum up, I overcame these three limitations of liquid bulk gallium through the LMPC form, which made it possible to use gallium in reconfigurable systems. So in my first study, I used the mechanical stability of LMPC to develop a reconfigurable pressure sensor. Conventional fixed sensors face a trade-off between a high sensitivity and a wide pressure range, but this tunable pressure sensor delivers both. In my second study, I used the processing stability of LMPC to develop stiffness-tunable electronics. Until now, wearable and portable devices had to exist separately, but this tunable ink lets you change the stiffness within a single device. In my third study, which is the last, I used individual uniqueness of LMPC to develop a reconfigurable security device whose key changes in response of heat. So this overcomes the limitation of conventional static security devices, which relied on fixed patterns and were vulnerable to duplication. So let's start with the first chapter, a tunable pressure sensor. The pressure around us spans a wide range, from very low to very high, and human skin can sense everything from light touch to strong forces across a range of 100 to 600 kilopascals. To mimic the skin's ability to sense pressure, many pressure sensors have been developed, but their performance was fixed. There was a fundamental trade-off. To get the high sensitivity, you should use a soft material so that it can change easily under a small pressure change, but then it could only measure a low pressure. To cover a wide range, you should use a stiff material, but then the sensitivity would drop. So there was a trade-off between sensitivity and detection bandwidth. To solve this, the stiffness-tunable pressure sensor, or STPS for short, emerged. In soft mode, low stiffness gives you high sensitivity. In rigid mode, high stiffness gives you a wide pressure range. So a single sensor can cover both, and the trade-off is solved. Due to this potential, many STPSs has been developed using various materials. But their stiffness tuning ratio was low, and even in the rigid mode, they were not stiff enough, so their pressure sensing range was still narrower than the human skin. So I overcame this limitation using gallium's high stiffness tuning ratio. Fabrication uses a T-shaped microfluidic channel. Uncured PDMS and liquid gallium go into the two inlets, and at the outlet, uniform gallium particles come out encapsulated in the polymer. Placed between the two electrodes, the LMPC becomes a capacitive sensor. The result is a high tuning ratio. In the rigid mode, where the gallium is frozen, it senses up to 1.45 megapascals. In soft mode, where the gallium is melted, it reaches a sensitivity down to 3 pascals. And these values represent a 141% improvement in sensing range and a 97% improvement in sensitivity over human skin. So across these two modes, the sensor surpasses what human skin can do. By adjusting the flow rate at the inlets of the T-shaped microfluidic channel, the particle size can be controlled. So I made a sensor with 3 different sizes and compared their sensitivity, hysteresis, and freezing point. All 3 values increased with larger particle size. So, size 1 had a drawback of low sensitivity and low freezing point, while size 3 had high hysteresis, which is why I chose size 2. And let me explain the cause behind each of these. Let's start with sensitivity. As I explained in the intro, smaller particles have higher internal pressure and a higher effective modulus, so they can resist compression, which lowers the sensitivity. Hysteresis comes from 2 sources, the viscoelasticity of PDMS and the plastic deformation of gallium, both driven by stress. The stress concentrates at the interface between the metal and the polymer. So for the smaller particles, which has their interfaces more spread out, show lower hysteresis. Next is the freezing point, which is the key for fast mode switching. Supercooling is when a material stays liquid below its melting point instead of freezing. This video on the right shows the supercooled water. So it stays liquid even below the 0 degrees Celsius, then start to solidify as the supercooling state is done by an external forces. Especially, gallium supercools strongly, so controlling this is essential for smooth mode switching. The smaller the particle, the stronger the supercooling. Many papers report that smaller particles have lower freezing points, and our own experiments confirmed it. Smaller sizes froze at the lower temperatures. When gallium freezes, it forms an alpha phase or a beta phase or others, but both have very high activation energy barriers, so gallium cannot easily freeze on its own. Instead, freezing usually has to be triggered by a nucleation catalyst, like an external defect or an impurity. The reason is that the smaller particle, the lower probability that such a catalyst can be present inside. And now you might think that smaller particles have more oxide, so the oxide layer could act as a starting point for nucleation. But The surrounding oxide is amorphous, so it cannot serve as a lattice template for freezing to begin. And it also blocks the particle from meeting the external defects. So, the larger the gallium particle, the more easily it freezes. To reduce the supercooling even further, I added iron microparticles directly to act as a nucleation catalyst. Mixing on iron lowers the energy barrier for nucleation, so freezing starts more easily around these particles. In our experiment, when we tried to freeze the samples at 23 degrees, only one with the iron actually froze. So comparing the performance to other stiffness-tunable pressure sensors, our sensor that we made showed both high sensitivity and a wide measurement range. And because the T-shaped microfluidic channel produces particles of uniform size, we could build uniform sensors and scale them up into an array. We then integrated this with a microfluidic temperature controller underneath to create a stiffness-tunable electronic skin. The temperature controller switches between modes by running cold water and hot water through it. So with this e-skin, electronic skin, we successfully sense high pressure like a baby weight in a rigid mode and small pressure like a heartbeat in soft mode. The second study is an electronic ink for making stiffness-tunable electronics. Conventional electronics have fixed mechanical properties. Rigid devices are easy to use, but uncomfortable to wear, while flexible devices are comfortable to use, but cannot withstand external force, which makes them inconvenient to use off the body. Stiffness-tunable electronics can adjust their stiffness, so they capture the advantage of both states. Conventional stiffness-tunable electronics were made by building a mechanical structure layer by using a stiffness-tunable material, and then stack an electrical functional layer on top. But this kind of multi-layer stacking made the process complicated and the final device very bulky. Gallium, on the other hand, has both high stiffness tuning ratio and high electrical conductivity. So gallium has the potential to perform both functions with a single material. But bulk gallium is hard to process, so until now, it has only been used as a thick mechanical frame fabricated by a mold. So to address this, I developed a gallium copper composite ink made by adding copper to gallium using tip sonication. This solved the ink's merging problem, which made circuit patterning possible. However, its freezing point was still similar to bulk gallium, so it kept freezing during the process, so I have to heat it constantly. The second problem is that when gallium stays in contact with copper, it forms an intermetallic compound, or IMC in short. So in this paper, I measured the diffusion speed, and based on that, you can calculate how fast gallium diffuses into copper. And for 5 micrometer of copper, it fully converts to IMC after about 3 years. So since this compound has a melting point above 260 degrees Celsius, once it turns into IMC, it loses its stiffness-tunable property. So to solve this problem, in this study, I developed a stiffness-tunable electronic ink that can be printed at high resolution at room temperature while remaining free from the IMC formation. The fabrication process is as follows. First, solid hydrophilic polyurethane is dissolved in dimethyl sulfoxide, DMSO. Liquid gallium is then added and dispersed into a polymer solution through tip sonication. The result is an LMPC ink with gallium microparticles dispersed throughout. Each gallium particle in the LMPC ink is covered with a 3 nanometer oxide layer. As you can see in the video on the right, the gallium oxide layer dissolves when exposed to acid. With the oxide layer, the particles stay dispersed, so the patterning is very easy, but there is no conductivity. Without the oxide, the sintered particles are conductive and freezes quickly, but it cannot be patterned. So, for the patterning, we need the former state, and after patterning, we need the latter, sinter state. Sintering research for making liquid metal particles conductive has been very active. I recently reviewed these various approaches in a chemical reviews paper together with Professor Michael Dickey. But the problem is that most existing methods require either a post-processing step or a special sintering agent. So to achieve this, I developed an ink whose pH changes naturally during the process. The key to pH control is the dimethyl sulfoxide, or DMSO. DMSO starts out neutral. During tip sonication, the temperature rises to its boiling point, and it thermally decomposes and releases formic acid, acetic acid, methane sulfonic acid, and sulfuric acid, which drops the pH to 5.5. After that, when the printed ink is dried and the DMSO evaporates, the weak acids evaporate along with the DMSO because of their low boiling points. But strong acidic compounds evaporate slower, so they stay behind, gradually lowering the pH down to about 1. So the initially dispersed gallium particles can be sintered together at acidic condition. And if you look at the graph in the bottom right, the gallium oxide layer dissolves when the pH is below about 3 or above 11. So now if this ink is used outdoors, acidic rain is around pH 4 and skin is around pH 5, so the external oxide layer wouldn't be affected, and which means that we can stay stable in most environments. Here's the process of making stiffness-tunable electronics by using our LMPC ink. First, in the printing stage, the ink is well dispersed, so it can be stencil printed or dip coated at room temperature. Then, during curing, the particles sinter, and the resulting stiffness-tunable devices shows high electrical conductivity and also a fast switching speed. We analyzed the conductivity of the device using 4-wire Kelvin resistance measurement. Rigid mode was higher, but both modes were on the order of 10 to the 5th Siemens per meter, and this is comparable to other reported LMPC inks. Also, even under strain, because the material is particle form, it showed a much smaller resistance change than the Pouillet law would predict. With the LMPC ink, we achieved high-resolution printing down to 50 micrometer, kind of like hair size, and we measured the bending stiffness of the device and used Euler equation to calculate the Young's modulus, which gave a stiffness tuning ratio of around 260-fold. Soft mode was similar to skin, while rigid mode fell between the Young's modulus of cartilage and bone. To make use of these two modes, we developed a stiffness-tunable neural probe as an application, and in its rigid mode, the probe can penetrate the brain without buckling, and in its soft mode, it cannot penetrate but instead causes less damage to the tissue. We then inserted the actual probe into the rat's brain. In the rigid mode, it could be inserted stably to the target location, and in the soft mode, it showed less inflammation than a conventional stainless steel probe. And thanks to that it has soft mode, the probe could still measure brain signals reliably even when stretched. And beyond the implantable devices, we also made a skin-attachable wearable device. In the rigid mode, it provides portable interface like a phone that is easy to use, and in soft mode, it works as a wearable that can sense the skin signals. Okay, let's move to the final study. The final study is a key-tunable security device that makes use of a unique per-particle properties of LMPC. The security system we made is an unclonable device. Conventional authentication methods uses serial numbers or holograms, but their patterns were too simple, which made them easy to duplicate. To overcome this, the physical unclonable function, or PUF, has emerged. During the fabrication, a random structure forms, giving each device a unique pattern, like a fingerprint. So when you apply an input called as a challenge to each puff, it produces the response unique to that device. These challenge response pairs are called CRPs for short. So when a puff has more CRPs, it means that it becomes harder to clone and its security gets stronger. So a lot of previous research focused on increasing the number of CRPs, and the most common approach was multiplexing. It came in two main forms. In a multi-level puff, a single challenge returns several different responses. In a multimodal puff, several challenges each return their own response. And either way, the goal was the same: pack in more CRPs. But even with more CRPs, conventional puffs have one key limitation: they were static. A static puff is deterministic, meaning that the same challenge always returns the same response. This static nature makes them vulnerable to machine learning attacks. There are two reasons. First, it is easy for an attacker to collect CRP data. And second, there are no conflicting CRPs to disturb this learning. So recently, in one case, a 512-bit puff was modeled with 97% accuracy in just 33 minutes. So to solve this, I made a puff whose CRPs change in response to the temperature, and this puff is hard to clone both physically and digitally. Let's start with how physical cloning is prevented, which comes from the fabrication process. My puff is made by dispersing gallium and filled metal into a PDMS polymer through vortexing. The particles formed this way all vary in size and composition, which makes them hard to copy. And in their liquid state, the two metals look identical to the eye, so you cannot tell the composition of each particle by just looking. But because gallium and filled metal has different specific heats, so particles with more gallium heat up slowly, while particles with more filled metal heat up quickly. So when you apply heat to the puff, each particle rises in a temperature at a different rate, giving each puff its own unique thermal pattern. Next is how digital cloning is prevented. So in my puff, the CRPs are only accessible during a specific window of time, and the real key is disguised among the fake CRPs. Here's how it works. When you set a start temperature and an end temperature of the controller beneath the puff, you create a window in which the temperature changes. So at the start temperature, all the particles are at the same temperature, so no thermal pattern appears, and no meaningful keys comes out. While the temperature is rising, each particle heats up at a different rate, so a unique thermal pattern, which is the key, is generated. Once it reaches the end temperature and settles into the thermal equilibrium, the particles are at the same temperature, so once again, no meaningful keys comes out. This means CRP data can only be collected during the limited window. On top of that, the key changes depending on the starting temperature, so without knowing the exact temperature protocol, you cannot tell the real key from the disguised one. These two mechanisms together form an effective defense against the machine learning attacks. This is a video of puff in action. When you place two different puffs on the temperature controller and set the temperature, a thermal pattern emerges as the temperature rises. So at the initial temperature, no key appears. As the temperature rises, the key appears, and once it reaches the final temperature, the key disappears again. In the previous video, the key was extracted from just a single point for simplicity, but in practice, raising the temperature once produces many keys. There are two criteria for reading the keys: the substrate temperature and the temperature range used to read the extracted IR video. Using these two criteria, the IR image is digitized and the response bits are extracted to obtain the CRP key. And let me explain why the key changes depending on the starting temperature. First, when the starting temperature is above the melting point, all the particles in the puff rise in temperature in the liquid state, so heating behavior is the same every time, which generates the reproducible and real key. The case where the starting temperature is below the melting point is different. Freezing begins at random location and times, and the particles don't freeze all together as one mass. They freeze partially and differently at each time, so as a result, a different thermal pattern comes out in each cycle, reproducing a non-reproducible key. And that's exactly the fake key, which is used for disguise. We evaluated how effectively these two methods defend against machine learning attacks. A model trained on the real key reached a CRP prediction accuracy around 80%. When the disguised fake keys were added, the accuracy dropped by around 40% point. And when we mix with the featureless keys that form during the constant temperature periods, these keys made up over 40%, bringing the prediction accuracy below 5%. And you can find the machine learning details on our GitHub, linked in the paper. To evaluate the puff performance, we measured the Hamming distance across 15 devices. We confirmed that each puff has high reproducibility and high uniqueness between puffs. To evaluate the long-term stability of the puff, we tested its performance for 13 days in a high temperature, high humidity environment. It maintained stable performance over those 13 days. And using PAX model, we can estimate that it can be used reliably for about 3 years of daily use. I think this is due to the self-limiting effect of the oxide layer. Based on the Cabrera mode oxidation theory, the native gallium oxide is electrically insulating, so it inhibits further oxide growth by limiting the electron tunneling. So in fact, even after 10 days of 60 degrees and 80% humidity, it grew by only 0.34 nanometers, and for a puff particle that's around 500 micrometers, a change this small is negligible. Finally, the LMPC puff is compatible with various patterning methods. Before the PDMS cures, it behaves like a liquid, which allows for stencil printing and molding. Using stencil printing, we printed currency, like bills that looks identical but carry unique thermal patterns, making them unclonable. This approach works not just for the currency, but also for logos or text. And through molding, we made a QR puff, so you can scan the QR shape to reach a locked website, and then read the puff thermal pattern to obtain the key that can open the site. In this way, we can be used to secure websites by using LMPuff. So in summary, throughout my PhD, I developed 3 different reconfigurable systems using LMPC. I hope that sharing this research can be a real help to your own work. And these are my first author papers I wrote during my PhD, so please take a look if you're interested in. So before I finish, I'd especially like to thank my amazing advisor, Professor Jeong Jung. And if you have any questions or want to reach me out, feel free to reach out at the email address here. I wish you all the best in what's ahead. Thank you for listening. Bye.